Hi there, I'm Clément. Today we're going to start a series of 3 videos on how to generate random numbers on embedded systems. Throughout this whole series we're going to be using the NRF52 development kit. That's because I got it and it's fairly affordable, and that's an ARM Cortex-M4 in it, so that's quite standard actually. Hey there, Clément from the future here. I know that the NRF52 got a true RNG generator inside of it, but that whole series of videos is designed for microcontrollers that don't have such hardware. Typically the time that I had to develop it was on an STM32. Many other microcontrollers don't have such things. So don't freak out if you know more about the NRF52, that's just an example. Now, back to the video. Now, first of all, the question before figuring out how to do that is why? Why would we want to generate random numbers? Well, first of all, maybe you're trying to design some type of a game or some kind of a human interaction, and in that context, you're going to want to create some randomness to keep the human entertained. I'm thinking about, for example, Simon Says. You're going to have to generate a random pattern that the human is going to try to repeat. In that precise case, you're not going to need specifically great random, because humans are not really good at identifying patterns, especially complex mathematical patterns. So there you could get away with suboptimal randomness. But there is another factor that randomness becomes useful for. It's going to be security. When you want to generate security keys and seed and use a cryptographic algorithm, there you're going to need randomness, and actually really good randomness. In this first video, we're going to introduce the concept behind randomness and how to test for it, and we're going to see a small demonstration. In the next videos, we're going to see how to generate better random, and then how to generate a lot of good random in the last one. So, how could we generate some random numbers, however random, on an embedded system? There is a issue in embedded systems that we don't like randomness. We want them to do what they are designed for, what they are programmed for, and we hate random events. So processors in general are always designed to be the most reliable and consistent as possible. So in the embedded world, we're not really going to be able to find randomness within the microcontroller. We're going to have to look outside of it. That outside is going to be relying on many phenomena, physical phenomena that we can measure that got some element of randomness. In the next video, we'll see a bit more about how and which one of those phenomena can be interesting to measure and to use as a source of randomness. In that precise case, for now, we're just going to use an ADC inside of the NRF52 that is not connected to anything. It's just open, and we're going to measure it. As we'll see, there is some noise on the measurement. Actually, on that specific one, quite a lot of noise and quite a lot of randomness that we can extract from it. But first of all, we're going to have to see how do you quantify randomness? How do you know if a series of numbers is really random or not so random as it turns out? Throughout this series of 3 videos, we're going to use one tool that is called ENT on Linux. You can install it, for example, on Ubuntu, apt-get install ENT, and you get the command line. That program needs a file as an input. That file needs to be a binary one, in which we got our stream of random numbers, supposedly random numbers. And then it's going to run a certain number of tests that are going to qualify different aspects of the random strings that we get it. All the links to those programs and different systems are going to be in the description as always. This system is actually going to run 6 tests in total on our random string. The first one is going to be measuring entropy. I'm going to leave a link in the description about how entropy is measured and calculated, but the result that you're going to get is going to be a number of bits that are going to be random, considered as truly random within your stream of bytes. In our case, for example, we are going to get 5 bits of randomness. Knowing that our data is cut in bytes, that means that we can get up to 8 bits of randomness in each byte. In the ADC default version, we get only 5 of them, which actually is a lot more than what could have in other applications on other microcontrollers. I suppose that this microcontroller is very noisy when it comes to ADC, which would not surprise me. That's not necessarily the core feature within the nRF52. So I'm not too surprised to see an ADC that is noisy. So that specific measure of entropy, the higher, the better, and the maximum that you could get would be 8 bits of randomness out of 1 byte. The second measure that you're going to get is going to be called compression. That one is, from as far as I understand, just a repackaging of the entropy measurement. When you get a fully 100% random string, it is impossible, it is mathematically impossible to compress it, because each and every bit of information is new and you cannot predict it in any way based on the past or the future or whatever. It is random. Thus, a fully random string is not going to be compressible by 0% is the max you can compress it. So in reverse, if we get only 4 bits of data that are random out of every byte, that means that we get only 50% of new information within each byte. That means that we got 50% that we could theoretically predict. And in that specific case, we would get a possible compression rate, theoretical compression rate, of up to 50%. So compression, as far as I understand, is just another way of thinking about entropy. In our case, the lower, the better. Then, the third test, which is going to be the chi-square. That test is a very standard test that is usually used to figure out if the measure that you got from some experiment, how close it is to what you would have expected, and to know if the differences are due to some random factors or if it's due to another trend, something else that would prove that your expected values are not as they should. In our case, we're using it a little bit in reverse compared to how it's used in physics or biology, where we are only focusing on the randomness. The randomness is the goal. You need to be careful with that test because it's extremely sensitive. And from what the documentation of the tool is saying, if you get between 0 and 10% or between 90 and 100% at that test, that random is not great. So in reverse, between 10 and 90% would be what you would want to get. I'm going to leave in the description a link to a video that explains that test extremely well, way better explanation than what I had during my engineering classes. The next step is going to be the arithmetic mean. Then the idea is that you got an entire range going from 0 to 255 when it comes to bytes. You could create some really good random, like really perfect random, that is going to be only between 0 and 100, for example. That's perfect random, but you're not using the full scale. That test of arithmetic mean is going to allow us to detect those kind of stuff. Are we generating good or bad random, but is it shifted towards the lower values or the higher values? We don't really know. That test is just the regular average, and you're going to know if your values are balanced on each side of the scale. Although you need to be careful with that test, that it shows you that the values are balanced on your scale, but it doesn't mean that it's using your full scale. Typically, you could have values that are balanced around 127, but that expand only on 50 on each side, and so you get a margin at the end that is never used, for example. That would be bad also. So you need to be careful about that test to actually be balanced, but it's not a proof that you're using the full range either. Then the next test that is being done is going to be the Montecarlo Pi Estimation. In that test, you're going to simply take your supposedly random numbers and simulate them, dropping them onto a square with a square like that with a circle inside of it. And you're going to throw your numbers based on their values inside of that square. Some of them are going to fall inside the circle, some of them are going to fall outside the circle. Depending on the ratio between the one going inside and outside of it, you're going to have a way of measuring actually pi or estimating pi. If you get some perfect random, you're going to get a very good approximation of pi. If it's not that good, well, the approximation is not going to be that good. And finally, the most important in our case, all the other ones are important for measuring your randomness, but embedded system and the way we're going to use to generate that random is especially weak when it comes to serial correlation. To generate our random numbers, we're going to measure physical phenomena. Those phenomena are kind of random, but not fully random. Typically, if you think about the wind and the direction of the wind, it goes in one way, it goes in another way, it can be random. But it's not going to go from one direction to another instantaneously. And to be really random, it should be able to do that. But no, a physical phenomenon like the wind is going to move towards that direction. And so you know that when it's turning clockwise, for example, it's most certainly going to keep on going clockwise or come back, but it's not going to turn 90 degrees all of a sudden. That means that there is going to be a high serial correlation in the measurements that we're going to make. Even though they are random at a higher scale, at a lower scale, they are not that random. If you think about an image, for example, there is a huge amount of serial correlation inside of an image. That's why we got so many algorithms to compress them that well without degrading them too much. So we're going to have to keep an eye on that one and keep the serial correlation as low as possible. One way of doing that is going to be to combine multiple phenomena that are supposedly not correlated and to find a mix that improves stuff. In the last part of that series, we're going to see a technique that allows us to get really, really good serial correlation, or actually no serial correlation, for actually not much space on the device. But we'll see that in the third video. So in that case, we're going to, for that video, just start by measuring the ADC and applying those tests to see how good or bad it is. It's certainly going to be bad. We're not doing anything fancy here. In my case there, I'm going to just ask for around 1,000 samples. You need to keep in mind that the higher number of samples, the better. The question is how much is enough. Knowing that we are using bytes in that case, each byte is going to be 256 on the total range. That means that if I ask for 1,000 samples, each and every value inside of a byte can be measured up to, on average, in theory, 4 times in my sample. That means that if we are missing 1 value, for example, we get 3 instead of the 4 we were expecting, we got 25% missing, which is a lot as it turns out. And the chi-square test is going to go crazy immediately for very small changes. So if you want to do really good measurements, you're going to need a lot of measurements. Typically, if you want one missing value to have a 1% change on that specific value, you're going to need, 100 samples for each one of the possible values. That means that for 256 possible values, you're going to need 25,000 samples. For those videos, we're not going to wait 25,000 samples. I'm just going to do 1,000. That way it goes quite fast and we don't have to spend too much time. Anyway, if you want to apply it, you're going to have to do your own test because your systems are different. Your ADC is not the same. Your environment, temperature, all those factors are going to play. So you need to test your own system. Another point regarding how I'm going to test that. For those of you that are used with embedded system, you will know that sending raw bytes through a serial communication is tricky, especially for the 0 value, because the 0 value is the value of \0, which is the end of string. So usually those \0s get not to be transmitted by the serial communication, which is not what we want. We want to see those 0 values. In our case, we want to see all the values. So what I'm doing in that case, I'm asking the microcontroller to send me each new sample as an X value that are going to be piped into a file. And then I got a small Python script that changed that X file into a proper binary file. And then we can give it to the testing system. So in that example, I just reuse the successive approximation ADC example from the nRF52 SDK, in which I just modified the timer time. We can modify it as we want. So there I put it for 100 milliseconds between every measurement. And then we got the ADC callback, which is just, instead of displaying the samples that we get, I'm gonna pipe them to a random number generation function that I created. That way, my code is separated from the standard code. And in that function, well, all I'm doing is just displaying it. For now, that's all we are doing. And then we use the Python script to analyze that. Let's run it, and we see the results. There, for example, we can see that we got 15, 14, 14, 14, 12, 13. A lot of values are bunched up together and they seem to be very close in the same time. Then it moves back up, back down, and so on. So that series of numbers, we can already see that there is a strong serial correlation, and we're going to see it in the results afterwards. We need to go to a sample. Who's there yet? Who's there yet? Yeah, we are at 1000. So we can stop collecting, and now we can run our analyze script. That is just gonna take our file, create a raw data file with the data, and call automatically the testing tool on it. So there, what we can see is that we got an entropy of almost 5 bits per byte just by reading the ADC, which is actually impressive. I was more expecting a number like I used to in other projects of around 2 bits, 3 bits, something like that. 5 is nice. We can play well with that. So then we get the compression. So I suppose that if you do the math, 5/8, that's going to be around, then that means 62% of a total byte. So I think that's going to be the same value represented differently. For the chi-square, we get a value that is less than 0.01%, which is extremely bad, as we said previously. A good value should be between 10% and 90%. Too high is bad, too low is bad. The arithmetic mean value, there, as we saw, our values, we're just measuring the noise on an ADC when nothing is connected. So we expect the values to be close to 0. We like the fact that it's moving, but we know that it's not going to go really high. And we can see it here. The arithmetic mean is going to be 31. Should be 127 in our case on one complete byte. Montecarlo simulation for pi estimation, we arrive at 4. That's indeed a rough estimation of pi, not that great. 27% error in that case. And then the serial correlation, even as humans that we can see, there is a strong correlation within the stream of samples. We get a correlation of 92%. That is extremely high correlation. So there we have it. That system is certainly good enough for actually fooling some humans in a silent says game. But that's all we're going to have time for in that video. In the next video, we'll see how to improve that, how to mix other sources of randomness, and just get better results on those tests. See you. Pauline is getting bored. To the ninja, and then she's going to be editing, and she's going to be like, oh, he's moving a lot. He's not stable. Why are you blurry?